So in this video, we're going to talk about directional derivatives and gradient vectors. Now, first things first, let's take a minute and recall what f sub x and f sub y represent. Remember, these are the partial derivatives of f with respect to x, and then partial derivative of f with respect to y. And what that means is, when we talk about slopes, specifically coming from a derivative, we're talking about the direction that we're approaching a certain place on the surface. And so f sub x, if you remember, was always parallel to the x-axis, and f sub y was parallel to the y-axis. When we discussed limits, prior to discussing these partial derivatives, we discussed how there were infinitely many ways you can approach a certain point, and then we went ahead and talked about the partial derivatives with respect to x and y approaching along these pathways parallel to the x-axis and parallel to the y-axis. Now we're ready to introduce this directional derivative idea. This is going to allow us to find what we're looking for using the derivative approaching in any direction. And that's going to be the big thing with this, is now we're not handcuffed specifically to a certain parallel to a certain axis. We can come in at any direction. Now, before we get into actually computing these directional derivatives, I want to mention the gradient vector. We'll use this gradient vector a lot moving forward. The notation for it is an upside down triangle with an f for function f, said gradient f. Sometimes you'll hear it called del f, but you'll hear me say gradient of f. This is actually a vector consisting of the components f sub x, f sub y, and f sub z, given we're in R3, of course. This vector is always going to point in the direction of maximum increase. Okay, so this gradient vector will always point in the direction of maximum increase. Now, taking this, we can now use it with our formula for a directional derivative. So the directional derivative notation will be this: capital D with a subscript u vector f of AB. This is going to be found by taking the gradient of f evaluated at AB, dotting it with a unit vector. Okay, so it's important to remember that that is a unit vector. Now, what it actually is going to represent is going to be a little more clear to understand once we take a look at an example. But for now, I just wanted to point out how we're transitioning from what we learned earlier into this idea of a directional derivative. The gradient vector can be found by this, which will always point in the direction of maximal increase for the function, which I also might add that if we take the magnitude of this gradient vector, that's going to be our maximum slope on the surface. That's something interesting to think about as well. And then putting it all together, we've got our directional derivative formula where we have the gradient of f evaluated at our point, dotted with u, and u being a unit vector. This will be the directional derivative in the direction of u. All right, so here's a look at a problem that will hopefully clarify what the directional derivative is giving us. It's really no different than before. It's just going to take a little bit of a different approach. So here's our surface. We're interested at this point in this direction. Okay, so let's go ahead and proceed with the formula that we talked about a moment ago. We'll start with the gradient of f, and that was going to be the components, in this case only x and y, f sub x and then f sub y. So the partial of f with respect to x, in this case, would be e to the x cosine y. And then this component would be the derivative of f with respect to y. So that would be a negative e to the x sine y. We'll take this gradient, we'll evaluate it at 0 pi over 4, and that's going to give us, for the gradient vector, 1 over root 2 and negative 1 over root 2. Now, we would need to take this and dot it with the unit vector. Now, we're given 5, negative 2, which is actually not a unit vector, so we would need to normalize it. So u would be the 5, negative 2 multiplied by 1 over the magnitude of that vector. And so the magnitude of it, if you remember, this would be 25 if I square it, plus a 4 if I square that. So that would be a root 29. So our unit vector would be 5 over root 29 and negative 2 over root 29. So I'll take these two things. The dot product is commutative, so it doesn't really matter the order you dot them in. But we'll just go ahead and write it in this order here. So it's a 29. And so if I go ahead now and dot that, that's going to give me a scalar. It's important to understand that's going to be a scalar, and you'll end up with 7 over root 58. Now, much as anticipated, doing this is not very difficult, but understanding what it is you found is going to be the big takeaway. So what we've just found is the slope of the tangent line to F through point P in the direction of V. So this guy here, it's a directional derivative, so it's going to be a slope. It's a slope of the tangent line to function F through point P and in the direction of vector V. Now remember, we turned vector V into a unit vector, but that doesn't change the direction. It only changes the magnitude. So this is the slope of the tangent line to the surface through the point 0 pi over 4 in this direction. And that's the big part that's new, where we're now specifying a certain direction using a vector to help us along the way. All right, so another really important property of these gradient vectors, if you'll remember earlier I said that the gradient vector is a vector that always points in the direction of maximum increase. I also mentioned that the magnitude of that vector would be the maximum slope that you would encounter. One of the more important ones is now the idea that gradients are always normal to level curves. And so let me show you what that means. Now, the example we're going to look at is x squared minus y squared, and we're going to talk about this point right here. So first things first, let's go ahead and find the gradient of f. So the gradient of f would be the partial of f with respect to x, and then the partial of f with respect to y. So that would be our 2x and our negative 2y. If I evaluate this at 2, negative 1, I end up with a vector 4, 2. So this vector right here should be a normal, should be perpendicular to the level curve of this surface that's being constructed through the point 2, negative 1. So if I take the function here, 2 at 2, negative 1, so I'm going to plug in a 2 there, I'll plug in a negative 1 there, that's going to give me a 3. So now I've got x squared minus y squared equals 3. So that's the level curve that this vector should be perpendicular to at this point. So this is going to be a hyperbola. And in fact, if we wanted to go a little further, we could say that this is x squared over 3 minus y squared over 3 equals 1, where our a squared is equal to our b squared, in which case all of those are going to be giving us an a value of the square root of 3 and a b value of the square root of 3. So the reason why that matters isn't so much because of the graph, but I want to make an example for you to show you how this should be perpendicular. So if I sketch this, then I've got something that looks like this. And this guy right here, that's going to be the square root of 3, or approximately 1 point something. And so when we take a look at our point 2, negative 1 point something, that's going to be beyond that and then down. So we're talking about in this neighborhood here. So our actual point, let's say point P is right there. Then if we take a look at this vector, 4, 2. And so 4, 2 would be from here over 4 and up 2. So proportionally, kind of follow me here, over 4, up 2 might look something like that. And so if I sketch that vector here, it's pretty evident that at the point P, where we might have a tangent line, that these two things right here would in fact be perpendicular. And that should be the case every time. Again, the gradient vector is going to be normal to all of the level curves of this surface. The one specific level curve we were interested in was this guy right here. So that's why we evaluated and we came up with a specific vector in blue.